is for old people.
Yes, and now we are starting a webinar. So welcome everyone, you who are here in Zoom and you who are following us at YouTube. We are happy to have another webinar in this FibRe and Treesearch online seminar series. And today we have the speaker, Professor Daniel Söderberg from KTH, and we will soon have a short introduction to him. We also have Per Larsson and Professor Eva Malmström here from FibRe, who will help us with the discussion afterwards. And if you have any questions, you can type them either in the chat or the Q&A in Zoom. If you're following us to YouTube, you can use the live chat. So you can type it at any time, but we will handle any questions after the presentation. So with that, I'll leave the word to Per, who will introduce our speaker.
Thank you, Josefin, and again, welcome all of you online. So normally the FibRe Center Director, Nat Larsson, greets you all welcome, but unfortunately she's on sick leave, so I will do that job today. And to make things even more complicated, we have a research area leader, Roland Kadar, who has invited today's speaker, but unfortunately he has teaching. So I will do my best to do both these persons' tasks. So without any further ado, I would like to welcome the Treesearch Director and Professor Daniel Söderberg as today's speaker. So Daniel, he has a background in fluid mechanics, typically applied on fiber suspensions. And this, combined with advanced characterization techniques, is used in his group to study and develop new and improved industrial processes and materials. And today, Daniel has a title for his talk, How Mechanism Controlling Microscopic Fiber Suspension Impact Nanofibrillar Systems. So, Daniel, please, the screen is yours.
Thank you. So I actually, hello, and thank you for the, you can see the slide now with my title. Yes, it's fine. Just thumbs up, Josephine. Good, so I will talk about how the title is trying to merge two of my research interests coming from the side of a lot of paper making and paper processes, working still with some of that, but also with nanofibrillar systems like cellulose nanofibrils. And sometimes it's good to merge disciplines and try to learn something new. And this is a little bit the focus of this presentation, trying to see that we can actually take things from the large scale, apply it on the small scale, and that will actually change how we should use our primarily our knowledge when it comes to behavior on the nanoscale for polymeric systems that are semi-flexible. The starting point is I took two images. I've forgotten to tell them where they are from. This is from working very closely with Professor Lars Wågberg at KTH. There is an interest nanocellulose has been an interest for a long time in our department and in Sweden, and actually in the world, and we can see here we have a nanoscale dispersion or something that we want to call it. Typically we call it dispersion. You could call it suspension if you want to. And it's nanoscale, it's fibrils. It kind of looks a little like fibers if you scale it up 1,000 times. And the interesting part of this that we have been using a lot is that these systems are switchable in the sense that if you have a charged cellulose nanofiber, which is on the right photograph, we can see that we have a 3 grams per liter, so 0.3% cellulose nanofibers in water. And at pH 7, it's a liquid, looks like a liquid, behaves like a liquid, looks like water actually. And to the left, it has been gel locked, because then what has been done at the charges of this the system is to the right charged, which means that you have a stable dispersion, and then you are screening the charges, and then you get a gel from that one, so which is not flowing, and that can be applied in a lot of different means. I want to start with why we are into this thinking and discussion at all is that if you do this and you just take your liquid nanocellulose dispersion in a syringe and you push it out in a bath, and that can be a lot of things in the bath. It can be ethanol, it could be salts. You will get a string. So the liquid you have in the syringe, when pushed out through the syringe or needle tip into the bath, you are getting the gelling behavior, and suddenly you have a gel string. And this was sort of pioneered by Walter, both Andreas Walter and Nisugai in Japan. It's more than 10 years ago now. And we were looking and working in the same area, and we were thinking about how could we do something on this of aligning and spinning nanocellulose dispersion into threads and filaments. And we came up with this. I won't go through the details of spinning because I've had that so many times, but just we had an idea of merging process technology, a little bit of fluid mechanics with the colloidal knowledge that we have with Lars Wågberg present and his PhD student, together with our PhD students. And this is depicting how we did it. We take our nanocellulose dispersion at this point, about 0.3% concentration. It's pumped now in a system, and typically this channel is about 1 millimeter wide. It's not very fast either, you're pumping. And what you do is today you first detach it using a microfluidics concept called flow focusing. You detach your suspension or dispersion from the walls by a liquid water layer. In a second step, you actually align it more, you enhance the speed, you get an elongational flow, and you are then adding, in this case, a proton system, so an acid that diffuses protons into the gel string, which causes the gelling. So the idea is that we can then lock the dispersion with aligned fibers, nanofibrils, and in that way get a strong final material. And that proves out to work out. But then, yes, you can do things in the lab. And something that we sort of start to understand is that we need to develop this further into an industrial process. We need to be even more able of controlling the system to allow continuous fabrication. And one thing that we are good at is that we know that if we have flow fields, and this is 100 years ago, Jeffrey published this about how flow fields align and affect single fibers, or actually spheroids, fiber-like particles in a shear flow. This can be applied for a lot of different types of flows. It's not only shear, but just showing how it looks like when you're shearing. If you are applying the Jeffrey theory, you can see that you get an aligned system. So that is something that we knew, and we thought, or actually think, that this is the key to what I previously showed with this alignment of fibrils. And of course, I want to point out one thing. Being a little bit of a teacher here, I just want to throw in something that I see a lot in various publications, a misunderstanding about shear and alignment. It's more delicate than you could imagine. Here I see, in this image, it seems like I'm saying that shear only aligns. It's really not 100% the truth. If this is then depicting what happens in a syringe ejecting into a bath, we see a flow profile, that is the arrows. I will just take out this annotation tool. So we have a flow profile inside here. And that is so-called Poiseuille flow. If we don't have too strange rheology, it's parabolic. What we also see, which is color-coded, is the shear levels. So we can see that the maximum shear occurs at the surfaces of the wall. So here we have orientation of fibrils or fibers, as we saw previously. Just want to note that in the center, there is no shear. So the idea of having a pipe for achieving an alignment throughout the system, it's actually totally wrong. There are kind of a lot of publications that don't even get this correctly. Shear is happening at the surfaces. It doesn't happen at the center. There is no alignment taking place here. So If we instead look at the system with the flow focusing, and to the top, we are seeing just a simple system with one channel, one acceleration. If you do the same calculations quite simply and looking what happens, we will see that in this case, inside here, there is still a Poiseuille flow. What we achieve here is a strong alignment because we're then creating this central stream. And here we can see that these arrows here in the center are actually about the same length. And it's accelerating, which means that we have what is called elongational flow. In this case, the maximum shear is still found at the walls out here, but here we have no fibers or fibrils. Fibers are only inside. But the elongational flow is the one that creates the strong alignment. And from one perspective, it's not the shear that creates alignment. It's actually so that shear is consisting of two different types of deformation. It's a elongational flow and it's rotation. So elongational flow that we can set up here is the perfect of achieving alignment. So that was a little bit on the sort of side of the presentation. Sorry, everything crashed. So I'm back. When we spin this, it's how we do it. We spin out in a bath. You build a system that is flow focusing. It's only water. You're doing your diffusion of screening agent, which is either protons or salts, into the gel thread. You generate this fiber. And for a long time, it looked like this. So when you do this, you can actually see that this is how we did it. You spin your filaments with the flow focusing device and you take it out by hand. This, of course, works and if you just want to look at the potential of what you're doing. And what you get out is actually nice filaments. When it's working, it looks like this. Filaments are typically slightly less than 10 micrometers. When it's successful, when you get good properties, it seems also to be correlated that they are very cylindrical and nice. They can also be collapsed and have a totally different cross section, and that seems, and this is gut feeling, to be correlated with poorer strength performance. All of this was done, given an idea of based on microfluidics and that we have this colloidal control with the diffusion of ions or protons. And this is what we developed as a theory that we can set up the key parameters that controls what's happening. So we have a system here with isotropic fibrils. We are doing the acceleration here, which align them. We are adding the diffusion of the protons coming in here that gels everything. And we are all the time fighting against de-alignment because on these scales, we will have rotary diffusion, Brownian motion affecting the system. And this is, of course, this is how we depicted it. And you can calculate some time scales and realize you can't just do it. You need to be correct when it comes to how fast you pump, what are the dimensions, geometry, and what is the concentration. And doing this, you're starting to think more and more about, can we do it typically faster? And the key that we have landed in this is an image made by my colleague Thomas Rosén, which Mr. Jeffrey and Mr. Brown. And this is the balance that we are trying to handle. We align with Mr. Jeffrey, and we have Mr. Brown diffusion that is counteracting everything we do. And you could argue that it's not a problem if we just do it slower. Its diffusion is faster into the system. It diffuses for a longer time, but then we get poorer alignment and we get poorer production capability. So we, from this, believe that we understand a set of things, and we don't understand the Rheology. It should be Rheology, of course. That's the flow behavior during spinning. We think that we understand the internal structure of the spun filament and this alignment coupling to flow, and we can control the interaction between fibrils. But why end up in this? If we want to go faster, you need to take what you know and apply it in a setting that allows continuous processing and preferably upscaling and speed. Otherwise, it will never leave the lab. So we have around 2 collaborative projects, KTH and RISE, and the first was a KTH project funded by Formas, and the second was funded by RISE and KTH. And this is called NanoC-Spin that was done at RISE. And this is then sort of the resulting upscaled capability. Still syringe pumps to perform the spinning, spinning into a liquid bath, trying to get this, all the steps, because you need to take away the water. And they are actually quite strong, these filaments, because they are still very low concentration of water. But of course, when you dry, you increase the dryness of the filaments. So we can spin something continuously. Everything should be fine. The thing is that it turns out you still need to start to think about this with what are really the goals. And the goal is of course, to preserve the performance we could get when we did it by hand. And that is related then to all of these parameters that I talked about. It's flow speeds, Brownian effects, Brownian motion. It will be about concentration. And we have then seen this, and we are trying to address a set of scale-up challenges that we need to solve. And one is parallel fabrication. I won't go through it here. Should be improved drying. And it has to go faster, and we need to handle the nanocellulose to have control. And that is much more to this point of understanding what happens and what are the similarities with the macro scale dispersion. We have an innovation goal, even though it's a lot of research. There is a US patent. We have a Knut and Alice Wallenberg proof of concept project at KTH for addressing some of these challenges. And then there is a startup that is trying to do this as a continuous, potentially commercial activity in the future. And all of this starts you thinking, what are really the effects? What is really controlling that? Sometimes we get very good performance, sometimes we get poor performance, and sometimes it's spinnable, so you can run the continuous spinning, sometimes it doesn't. And one of these keys is really what happens, what is the dispersion state, and that's the balance between Brownian motion and everything else. And I just took this image to show that Brownian motion is super important. This is from Tian et al, looking at Brownian diffusions of fibers in air. And what we have here is, to the right, we have a set of diameters. It is given by their simulation of nanoparticles. And then we have estimated time for one rotation in seconds. So this is actually, if you have a filament, it is the time it takes to go around a whole 360 degrees. And of course, since it's Brownian motion, it won't be just that it's rotating, it will jump back and forth. But the sort of integrated time for to do one flip 136 degrees is seen to the left. And that means that if we're working with something that has a diameter of 10 nanometers and an aspect ratio of 200, so maybe close to what a fibril is, we see that we have a time that 10 to the power of -5. So we're talking about less than milliseconds. And of course, this is actually in air. So for water, time is 50 times longer. It's an order of magnitude, but we're still talking that let a nanofibril be by itself. It will do one turn in it's hard to do a video of this in reality, but you can get what's happening. And it's doing exactly that. It's putting in a system, single fibril moving by itself. So from some perspective, this is probably fibril if it was alone. And as you can see, it's jumping around Brownian effects. It gradually moves, not directly one turn. It will do eventually. Actually, I didn't simulate this. I tried this myself, long enough to get one rotation. But this is then microseconds we're looking at it in time resolution. This is what happens in my nanoscale. And of course, if you start to add more filaments, you will have more things happening. We also start to see that we have interactions. That will affect the system. And to the last, it's the same concentration as the middle movie, but it's a very long fiber with very high aspect ratio. So this entanglement, the crowdedness of the system comes out to be very important. And there are to control this, and this is taken directly from what I've been doing on paper making side for a long time, trying to understand flocculation, which affects your paper structure and the paper strength performance. And if we then ignore scale, it's just a question about crowdedness. We can actually calculate this crowding factor by trying to calculate that how many fibers do we have in a volume. This is the length of the fibers. How many fibers do we have in a sphere that is set up having the length as the diameter of the sphere? So we have a fiber and we have a sphere that is the same dimension as the fiber. How many fibers at the same time do we have there? You can set up it's quite easy to calculate. It's something the students do at the course in pulp and paper making, pulp and paper processes, and try to deduce that. It's quite simple. You get an expression that relates your volume concentration to your aspect ratio of the fiber. It has no dimensionality. There is nano or micro or milli or meters or kilometers. It's actually not a big change. It's just a question about aspect ratio. You can also do another thing, and that is from the mathematics. If you assume that you have stiff, straight fibers, isotropically oriented in a system, you can estimate the number of contact points you have. And that is an effect then of the crowding factor and of the aspect ratio. And I was just one point. When we talk about contact points, just to be, this is sometimes seen from two perspectives. 4 crossings. This is 4 crossings, but it's 8 contact points. Each fiber has 2 contact points in this case. And contact points is then important. And typically when we do our spinning, we realize that we have about crowding factor of, it's very rough, maybe 30. And we have contact points about 1 per fibril. And that is a little bit interesting perspective, because if you have 1 contact point per fibril, you should theoretically then don't have a network. The threshold for any type of percolation in a network is 2 contact points per fiber. Otherwise, you can't get a connected system. In reality, I would say that it's 3 in a 3-dimensional system, but this is, you need definitely more than 1 contact point. Because if you only have 1, that means that you have 2 fibers in contact with each other and they won't have any other contacts. So they couldn't carry stress or anything else. They won't sort of have long range transport of load in the system. But it is more than just the contact points. And this is taking results from Daniel Söderberg in 20 years ago. and they did some modeling that was advanced at the time, looking at the idea of scale up of computational capacity. This was really good at the time. What they did was develop a system where you could model your fibers as a chain of rods. Nunchucks for some that looked at movies in the 80s. And then you have stiffness, and you will have interfibrillar forces. So you would have friction. And this is now macro scale fibers. So we talk about friction. And if you do this, you can actually see that with have no friction, you don't get any type of flocculation. But if you have friction, you get a flocculated system where you form bundles. And this is at very low concentration. So what they really showed us also that what happens is that friction, what happens in this system is that energy is stored in the elastic bending of the fibrils. We have then tried to start to think about what happens in a nanoscale system, so in our nanofibers setting. If you do rheology at a wide range of concentrations from 0.01 up to 0.3, you can see that you have specifically, I want to look at the storage modulus here, which is then the field symbols. We can see that at very low, we have a water-like behavior. And we can see that if you go up a little bit, you get some sort of elastic storage modulus, and then that goes down to water when the frequency gets high enough for oscillatory shear test. And then if you go over a certain limit, it sort of still continues to behave. And actually, this one falls down over here, but it shows that there is some switching. It's inelastic in some regions, and it's not elastic in others. We can then start to evaluate what about this with contact points. So we have done all of the experiments you saw was a lot of tempo CNF, where it was calculated distribution. So we have mean lengths of fibers. We get the dimensions both from scattering techniques and by measuring with AFM. You can start to estimate crowding factors. And for the system that we saw from the rheology measurements, we have a crowding factor going from 1 to 45. And contact points, there are never more than 2. So the system still is very, very low in contact. So why do we have a network system if we have too few contact points? The answer, it looks like this. This is going back. This is macro scale fibers done by Bill Sampson from the University of Manchester. He took normal pulp fibers. He colored 1/10 of them black. He made these suspensions so you could look into them. It's very low concentration. But this is about the same contact points that we have and crowding factor when we are spinning. So this is what the dispersion looks like if you're trying to make some sort of model of it. And they are clearly below the connectivity threshold because contact points are less than 2, but they are still forming a network. And the reason is the elastic properties, the semi-flexibility of these fibrils make them to get interlocked into a system at much, much lower concentration than you would if you have perfectly stiff fibers. And of course, if it was a very flexible polymer, you wouldn't get this behavior either. So by doing this, just illustrating, ending up, this is doing a little bit of just showing. To the left is 0.2%, and to the right is 0.3%. And yeah, we can see that big bubbles that have a strong buoyancy is rising, but we can see that the small bubbles stay. This should be this is not a connected system theoretically if you assume stiff rods. You need a semi-flexible system of fibrils. You need the possibility to have something that acts like friction in between. It's still a charged system, so it's not gelled, but it actually keeps small bubbles in place. So the conclusion we have is why and when do we succeed? It's about optimal conditions. We have a system that I talk about as a loose network, and the key is that it is a connected system. When you pump and you're doing the flow focusing and it's strong enough, your levels of shear and alignment, you are able to move the system. And that helps you also because it makes it take longer time for Brownian diffusion because of the interaction afterwards. And it's elongation and not shear flow that calculates this. And we have been doing quite a lot on this, and Thomas, in working together with me, has developed this technique using, we call it flow stop, it can be called stop flow. It's a technique where we start with the same type of setup that we have for spinning, but we're using this to try to quantify what happens to fibrils in the system. So you have a system with the flow focusing, you're running it, you have very good pumps that can stop it accurately. You are using a laser and polarization filters, and then you can see orientation by birefringence of the fibrils. So using these channels, what we see to the right is the birefringence signal. So that it's red means that it's aligned. And this is showing how it looks like with just by having light. So we can see the flowing in the flow stop. We see that it's bright because now we have a light. And in this small box in the center, we can see the intensity to the right in the graph. And we'll see what happens when you stop the flow. And that is the decay of Brownian, the Brownian-driven decay, but it's much slower than this millisecond. And that is related then to that we have an entangled system. I just want to point out that this came out as an interesting technique. It did not only make it possible to look at how this behaves, the flows. It also gave an opportunity using a DLS approach similar to the dynamic light scattering, where we can actually estimate the length distribution of a nanoparticle system if we know the diameter, the average diameter. And this is an example of trying to do that. And we can see that the length distribution for the CNC is different from the CNF. It's not a perfect measurement. It shows good similarities if you do this quantification by hand from TEM or AFM images, but it's rapid. It's a second thing on the second level technology. Just showing, and this can be done, and Thomas is using it for a little various sources. And what we're seeing here is another example of networking on this is various sources of MFC and CNF that is undergoing this flow stop. And what we can see is that you have totally different behavior. This is then related to the concentrations, the properties of the MFC, CNF. We can also see that we get spots in some of them, which is actually strong flocks or agglomerations. And this can be used to quantify various CNFs. And I mean, the basic idea that Thomas is working along is that we can use this as a readily usable method to quantify CNF dispersions, both when it comes to sizes, but also to their networking, loose networking ability. So this is seen as a possibility for process control. And how we want to use it is a concept called digital twin, and that has been published by Fredrik, who we're working to close together with and have done for all the time since Wallenberg Wood Science Center started. So if someone wants to read on how you can use this idea for nano process control and how you can sort of put these pieces together, I recommend this quite recent article in ACS Nano. And with that, I would like to thank you.
So we're open for questions to our speaker. We have one raised hand in the audience who has been raising the hand for quite some time. It's Thomas Larsson. I allow you to talk to see if you want to say something.
Can you hear me now?
Yes.
No, I can see you.
Yeah, I don't know if you see me, but if you can hear me.
Yes, yes.
But I actually had two questions, Daniel. First of all, when you show this continuous production of these CNF filaments,
Yeah.
I mean, the parallel is, of course, when you look at how, like viscose, and when you do spinning of textile filaments and so on.
Mhm.
One thing they use in order to improve on degree of order is stretching. I don't know about this wet CNF filaments. Is it completely impossible to stretch them? Will they break if you try, or can they be? I mean, to counter this Brownian thing, would it be possible to do some form of stretching on them?
Yeah, I actually think that some of the really good results on the Teshki got once upon a time is partly related and to that we are successful in putting them up, taking it up, and I guess that there is some degree of stretching where, because it has a weight when you lift it up, right?
No.
But since we don't have a coiled polymer, we can't. The fibrils are semi-flexible. Yes, like you know, one of these type of scissors you can have to pick up something on a far distance, right?
Mm.
Yes, you can stretch that for some distance, but we don't have the possibility to drag out a polymer. So I don't think that we can do at all the same as viscose or these high performance Cordenka materials, which is really based on that you have a long change polymer that you can sort of stretch out. It doesn't seem to work, and it's kind of strong when we spin out, but at 0.3 or 0.2%, it's not that strong. And we can't go up in concentration because you don't get any filaments, because then you have too much flocculation.
No, but I was thinking more about, you know, fraction of a percent or a percent or something like that. I mean, not the level that you use in textile filament spilling. I mean, but I mean, effectively, if you stretch it, it could be similar to just squeezing more water out or something like that.
Yeah, definitely, and I think it's happening already a little bit uncontrolled when we do this, because you lift it. That means that you're putting some force on.
Yeah.
So, but you're totally right. It's to be investigated, I think.
Yeah, okay. The second thing, I got the impression when you talk about crowding factors and contact points and so on, that if I don't misunderstand you, a CNF gel is actually one huge flock.
I missed you, Thomas, once again.
Yeah, a CNF gel is actually just one big flock.
But now you said something. I have to ask, what do you mean with gel? Would you mean the charge system or when you have screened the charges or protonized the?
No, when it's before you gel it, so to speak, when you still have it with charge active, so it's more of a dispersion or whatever you want to call it. In that case, since I got the impression that the number of contact points is too low, really, to be a network, but the impression was that it's okay, it still holds together and it behaves in a fashion similar to what you could expect from a flock. So I mean, it's actually one big flock rather than a dispersion.
Yeah, there is of course some sort of friction between the fibrils because it's bent in place, but it really, my perspective is, I think it's more flock-like network. That's why we call it loose networks. Flocks are not an accepted naming in the nano world yet. But I totally agree with you. This isn't it's really similar to paper making.
Yeah.
And the cool experiments would be if we could do systems where we could change the stiffness without changing aspect ratio.
Yeah.
Maybe you could do that with charges, but if you have different charges, you have processed them differently. So then you get different length. It's a difficult study, but I think there could be done, and we are doing things in this direction.
Okay, I have more questions, but maybe there are others that want to ask questions.
Yes, we have another raised hand by Lars Wåhlberg.
Aye. Now it's difficult.
Oh, we haven't. So, Lars, allow you to talk.
Well, thank you. No, it was a comment to Thomas' comment that a crowding factor doesn't mean that they are in contact, Thomas.
No.
Crowding factor larger than one, so that they can be in the same volume and just swirling around each other.
Yeah, but I mean, there have so many names floating around. We are talking about different things that are in different states, in different phases. We are talking about vase, we are talking about glasses, we are talking about etc. etc. And I mean, from this perspective, it shares quite a lot of similarities with what we commonly refer to as flocks, but at a different length scale.
No, a flock is an entity that is moving in as one body. And that's not the case when they are.
Well, if I move,
can I answer something in my seminar?
No.
Yeah, Josephine, take Thomas out for a second. So no, but it's fine. But I agree, Lars, and actually we don't know if on that level if we have something that is actually on a behaving like flocks. And I think that an interesting concept and I know that Malin Nordenström has used, and that is this not volume filling arrested state, but volume spanning arrested state is what we see, right? So it's like they are stuck together because they are mechanically interacting, and the flexibility is important. But we don't know if they on a nanoscale or micro scale form coherent bundles like flocks. I mean, that's yeah. We have a project trying to figure this out, but I totally agree. It's not. So when Thomas says one big flock, I would agree. But if you say that is flocculated on with a lot of flocks, no, we don't know that, and that's. Lars, what do you say?
No, it's not a flocculated system. They are swirling around each other, but if you increase the number of contacts, so they are really sliding against each other, then suddenly they cannot move, and then we have this. But I want to come back to maybe to the audience also to say what Thomas was talking about, the stretching. What we are striving for is a pre-orientation of the fibrils so that we can spin them from an organized state. So if somebody can come up how to do that, that would be good.
Yeah, and that's following how we do with aramide. I mean, you get the liquid crystalline state before you spin, right, Lars? So
yes. So I think that's definitely a good point.
I had the solution yesterday when I fell asleep, and I lost it when I woke up.
But can I come back with another question?
If there is someone else, they have precedence to Thomas.
Yes.
Yes.
Don't say any right now. Do you have? So okay.
So when you talk about this channel where you form filaments, it's you said it's not shear, it's elongational flow. Now we have talked about this before, and it seems that this elongational flow can be quite strong. I mean, when you do the homogenization, you can essentially rip fibers apart with this elongational flow. But do you have the same situation in this filament forming channel? If you increase the speed, so to speak, too much, can you start to rip the nanofibrils apart as well?
No.
No.
I think that there is a limit, and I think that we see that, and we have done this study with the sort of when we actually film what happened in a homogenizer. But then you get fibrils. We can't see them, but there doesn't seem to be you can't cut them down to a certain size, apparently.
Okay, thank you.
Good.
So, and there are others who are allowed to ask questions.
Jada has a question.
Yes, and we. See, where did you go? Allow you to talk.
Oh, thank you very much for your very clear presentation and fascinating topic. So I have more a philosophical question, and is regarding the interaction between modeling and experimental. Because like I see you have to take a lot of choice. So how you deal with the to build or to design the experimental using the modeling when you have to stop because the the model need a simplification of the system. So, and then you find out later that the model is not suitable. So what is your thoughts about how the two aspects of the science can help each other in progress?
Yeah, I think they are excellent as a combination. And one thing that we see when we try to understand this system is that doing this, we are working with not MD modeling, but trying to do the coarse grain, because you want more fibers, and that if you would have the water resolved, it would be a problem. But both to interpret the data that we get out. So you need models for all type of scattering techniques that are suitable for this. You need the models to understand your data. And then you need to complement this in some way to show that's right. I think I'm just citing Thomas Larsson now. If you have two methods showing the same thing, it's a good sign. And then I think that sometimes we model to, one of the beauties with science, I think, is to learn to reduce the system. And I know that Thomas has been working together with Ahmad, who is a PhD student, and looking at something called XPCS data. When you look, it's kind of like DLS, but using X-rays and not using spherical particles, but looking then at fibrils and spherical particles inside the fibrillar system. You can start with the complex model, but you can also identify that sometimes you can develop reduced models that capture all the physics that you see, and that is one of the beauties. You shouldn't have more models than what you need. So if you have a complex system, you can reduce it. Maybe you can identify the true mechanism that you need to model. You don't have to incorporate everything. And from an engineering perspective, I think that's super important, because in engineering you can't do the full systems. You need to find means of designing your processes and applying this that are good. And that, I guess that's why you have these handbooks once upon a time. Now we have the web with tables for things. I think the perspective that we try to do is to develop engineering knowledge.
Thank you. Thank you very much.
I have one or two questions, if I may.
No.
Well, thank you for the presentation, Daniel. So you mentioned the work on scaling this up and making commercial flow focusing. If I force you to pick one challenge, what is the greatest one to solve to make this happen?
I think that we share the challenge, and this is something for VVSC next period. I know it's one of the things we've discussed. And the main challenge for everything here is water. Whatever we do, and this could pay off also for paper making, whatever we do, you need to remove water. And that energy demand is actually, I think we have some means that I won't discuss here, but I mean, if the raw sort of estimate, if you just want to evaporate all the water I mean, we only have water. It's 0.2% fibers. So in principle, the only thing we do is evaporating water in the process, if in the crudest approximation. So it's important to find means to get water out without using heat. That doesn't necessarily mean that you should do solvent exchange, because that can be even worse, I've learned. This is an input, and we had a couple of master students working and talking to Ola Wallberg in Lund. And the energy cost for then, if you would do this with acetone as a solvent exchange, on the paper, it looks like an interesting idea. But then you have to handle, industrially, you would like to handle water acetone separation, and that is more costly than just taking away the water from the beginning. That's the biggest challenge.
So the short follow-up, I guess you already gave the answers. Are you sort of happy with today's CNFs, or what kind of CNF property would you like to change or have to spin even better material, or make it easier to spin them?
That's another. Now I have another question, but I think that's the second challenge is variability, that we are working with a natural material with a huge variability. I think that a lot of the experiments that are being made, specifically when we're looking at smaller dimensions, maybe not if you make a thick film, it doesn't matter too much, but otherwise, variability I think we have a variability in length distributions. We have a variability in properties. That is, for example, when you spin, super important because it's small volumes you're working with. Actually, just to get a figure of what we're doing, someone once said that, why are you spinning pulp fibers? Because they already exist. Yes, pulp fibers are 2 millimeters long, right? But if you do the calculation, you would, the estimate that I typically use is to say that one softwood pulp fiber gives, us 10 millimeters of filaments. So if we have one fiber that has one property, which is then from early wood, and then we had another fiber from late wood, and they probably look different when it comes out to the nanoscale, they might give different performance. So this of variability and control of variability is the second biggest challenge.
Thank you.
And if there's no more questions, I think we thanks our speaker. Thank you for a very nice presentation. And we also thank you who have been following us during this webinar. And there will be a new webinar in October, and you will find the date for that on the Treesearch website and or on the FibRe website. So please check that out.
It should be October 25.
October 25, Tuesday, same time. So hope to see you then. So bye.
Thank you.
Bye. Nu ska jag gå ut till bruket igen.